This is a question-answer session on the topic of thermodynamics. We shall discuss the following question, and here it is. A thermally insulated container of volume V0 is divided into two equal halves by a non-permeable partition. A gas is confined to one of these halves at a temperature T0. The partition is now removed suddenly, and the gas is allowed to expand to fill the entire container. The final temperature of the gas in terms of its specific heat Cv will be, the options are, if gas is ideal, and the options change to if the gas is real van der Waals gas, and the options will be if gas is a real gas obeying the equation of state given by. The answer coming up now. Let us show the initial state. This is a box, say. In the middle there is a partition that divides the box into two equal halves. If the volume of the box is V0, the volume of this portion will be V0 by 2, and the other portion, that is this one, will also be of volume V0 by 2. The left portion contains a gas of temperature T0. Let us mention that this partition is non-permeable, meaning that gas cannot permeate or go through this partition. The right portion is vacuum, contains nothing within it. Let the partition be removed suddenly. Such sudden removal means that the process of removal is an adiabatic process, and the container is thermally insulated, meaning that no heat can enter into the container from outside. Neither can any internal heat escape through it. Upon removal, the gas that was earlier confined to the left half would rush and occupy the entire container volume. So the volume of gas is now V0. Suppose the temperature of the gas in this final state is T. So this diagram represents the final state. It is a free expansion of gas to vacuum. Work done by gas is 0. So d cut W, representing amount of infinitesimal work, is 0, as vacuum does not oppose the gas. The chamber is adiabatic, so no heat exchange, no heat is supplied to gas. So d cut Q, representing infinitesimal heat exchange, is 0. Let us use first law of thermodynamics. dq equal to du plus dw. On transposition, we have du equal to dq minus dw. Now dq equal to 0, dw equal to 0. So du equal to 0 is a result of paramount importance, implying no change in internal energy. Let us now write down expression of internal energy of gas. Take internal energy U to be function of T and V. So du is del U del T at constant V into dt plus del U del V at constant T into dV. For this factor, let us use first law of thermodynamics that gives del U del T at constant V is Cv, the specific heat at constant volume. So du is Cv dt. Now let us look at this factor. We use first energy equation that says del U del V at constant T is T into del P del T at constant V minus P. So we write this expression here for the second term. This equation that gives the change in internal energy of system is crucial for the given three problems, and let us name it equation 1. Now consider ideal gas case. The equation of state satisfied by ideal gas is PV equal to nRT. We quote equation 1. Let us now find del P del T at constant V. What is P? It is nRT by V as follows from the equation of state. Partial differentiation with respect to T keeping V constant gives nR by V. Put it here in the second term, and for P put. Clearly these two terms cancel out and we are left with du equal to Cv dt. Integrate from I to F, I for initial state and F for final state. So integration from I to F over du equal to integration from I to F over Cv dt. Assume Cv is constant in the range of integration. So UF minus UI is Cv into TF minus Ti. Since there is no change in internal energy, that is du equal to 0. For this finite process, delta U equal to UF minus UI equal to 0. This means which gives TF equal to Ti. Now TF, the final temperature, is T and Ti is the initial temperature T0. So T equal to T0. Hence answer is option C. Let us now consider real van der Waals gas. The equation of state being, we quote equation 1. Now, what is P? This follows from the equation of state. Let us put this for P here. Partial differentiation with respect to T keeping V equal to constant gives nR by V minus NB. So let us rewrite du. It is Cv dt plus. This is the derivative that we got, and instead of P let us write as we got from the equation of state. Clearly they cancel out. Here we should have dV and let us insert it thus. So du is integrate from I to F. Integrate from I to F du. This will be integration from I to F over Cv dt plus integration from I to F over n square A by V square into dV. So UF minus UI equal to, taking Cv equal to constant, integration I to F dt plus n square A integration dV by V square, the limits being I to F. This integration yields UF minus UI gives, since there is no change in internal energy, du equal to 0. For this finite process, delta U equal to UF minus UI equal to 0. This gives, in this problem, initial temperature Ti equal to T0 and initial volume Vi is V0 by 2. The final temperature Tf is T, say, while final volume is Vf equal to V0. Putting these, we get this leads to T equal to T0 minus n square A by Cv into V0. This is the answer. So the correct option is, we next consider real gas obeying the equation of state. Let us quote equation 1. We shall now evaluate the factor del P del T at constant V. Now the expression of P that follows from the equation of state is, let us put it here. partial differentiation with respect to t at constant v gives. So du equal to, instead of p we put from equation of state. These two factors cancel out and we get integration from I to f du equal to integration from I to f cv dt plus integration from I to f a squared by v cubed into dv. uf minus ui gives cv is constant, so it goes outside. A square is also constant, so it goes outside. This integration leads to, so uf minus ui is, since there is no change in internal energy, du equal to 0. We have for this finite process delta u equal to uf minus ui equal to 0. So we have, in this problem, Ti equal to T0, the initial temperature, Tf equal to T, the final temperature, Vi equal to V0 by 2, the initial volume, Vf equal to V0, the final volume. So we get T equal to T0 minus 3a square divided by 2cv V0 square. This means this option is correct.